Okay, welcome back. We are looking at page 111 in the workbook, and on this page we're going to try to answer the question of how do we know when a vector field is conservative? Okay, that's important because we talked about how the fundamental theorem of line integrals is a very nice tool for calculating line integrals, but it only works if we can find a potential function, and that only happens when our vector field is conservative. Okay, so how do we know when we have a conservative vector field? Well, one way of getting at this problem is to introduce a notion of the curl of a vector field. Okay, and so we're starting with a vector field in 3 dimensions. Okay, it's got 3 components. And the curl of the vector field is a new vector field that has, this is its definition, a big long formula that's a vector that contains a bunch of partial derivatives in it. Now, this would be a really difficult formula just to memorize, okay, because it's got so many pieces to it. So there's kind of a nice way of arriving at it if we introduce a bit of new notation. That's this part here. Okay, you might recognize the upside down triangle as being part of our notation for a gradient. Okay, and so one way to actually calculate the curl is to define a new symbol, okay, the same upside down triangle that you use in a gradient, and we're going to define that just to be a vector that contains a bunch of partial derivatives without a function. Okay, whoops. Fix that. Okay, and this is called the del operator. Okay, so del is just our word. When we see this upside down triangle, we're going to write del. We're going to say del. Those of you physicists out there, you may have seen this notation already. It's pretty common in that subject. Okay, and it turns out we can arrive at this big long formula up here for the curl by thinking of a cross product. Okay, and I just want to illustrate that for you here. Okay, so del cross f. Okay, if you think about just the way that we calculated cross products of vectors, we did that by taking a determinant where we started with our first row being I, j, and k. The next row would be the components in our first vector, which is this del operator that we talked about. Okay, so it's going to be a bunch of partial derivatives. Okay, and then the third row is going to be just the components of f, which in the statement of this definition were given to be f1, f2, and f3. Okay, what would this look like if we expanded it out? Okay, well, let's just do an ordinary determinant here. Okay, so we'd start by kind of crossing out the first row and the first column. Okay, and we would get partial y times f3, and I'm putting times in quotation marks because it's really not multiplication that we're doing. We're going to take partial y of f3 minus partial z of f2, okay, and multiply that by I. Okay, there's the first part of our determinant. And the next thing we do is take a minus sign and cross out the row and the column with j. Okay, and then we're going to get partial f3 partial x minus partial f1 partial z j. Okay, and then finally we come to the k component, and there, cross out the row and the column with the k, we're going to get partial f2 partial x minus partial f1 partial y. Okay, and so we're just using the same process for constructing a determinant that you learned earlier. Okay, but is this the same formula as what we had above? So we've got something that's supposed to be equal to the curl down here, and our definition up here says that it should look like this. Are those exactly the same? Okay, notice there's a little bit of a difference here. Okay, but they really are the same formula if we do a little simplification here. Okay, let's take this minus sign and distribute it through. Okay, and if you do that and kind of reorder the terms, notice what happens here. We're going to get partial f1 partial z minus partial f3 partial x. And you can look up above and see that we've got a match now. Okay, so this last line that we just wrote down, that's an exact match to the definition up here, and it just illustrates that to calculate the curl, we can do it just by taking a determinant as we illustrated. Okay, now what does this have to do with conservative vector fields? Okay, well, we come to the first theorem, which is a test for conservative vector fields, and actually it's a test for three-dimensional vector fields. Okay, so start with the same situation that we did in the definition above, okay, with a vector field that has three components to it. And it turns out that that vector field will be conservative if and only if the curl is equal to 0 everywhere. Okay, so in other words, if I give you a three-dimensional vector field and ask you, is it a conservative vector field? Is it a vector field that we can find a potential function for? What you need to do is to go back and calculate the curl using this process, and it will be conservative exactly when you get a 0 for every term, okay, in this big long curl formula that we have here. That's our test to see if we have a conservative vector field. Okay, we'll do an example a little bit later on to illustrate how that works. Okay, there's also a test for two-dimensional vector fields to tell when they're conservative. The nice thing is that that one's quite a bit easier to write down than the previous one. Okay, so if you start with a two-dimensional vector field, something that just has two components, it's going to be conservative exactly when this one equation is true. Okay, the partial of f2 with respect to x has to equal the partial of f1 with respect to y. That's an easier check. And if that statement is true, you have a conservative vector field in 2 dimensions. Okay, and just maybe one closing comment here. You can actually derive this second theorem from the first theorem. Okay, and if you're interested in that, you can look at the written solutions, the bottom of page